Okay, here we go with lenses. Guess what? I'm going to try to make sure this time you guys can see the pen and everything. So I'll be moving the paper hopefully as we go down the page. So I know you couldn't see everything I was doing while I was doing it. So I'll be more careful. All right, for this one, you're going to need a ruler. We're going to be drawing some ray diagrams, and you're going to be shocked that ray diagrams for lenses are a lot like ray diagrams for mirrors. Unfortunately, I never got to test you on that. That's something I got to think about. Anyway, so we're going to have a look at that. All right, first of all, a lens is just a piece of glass or plastic. Think glasses in your eyes, or for your eyes. That glass or plastic that changes the direction of light. Oh, it refracts it. Refracts it. Okay, and this does this because it is made up of a different material than air, and so therefore there is a change in speed in the glass and therefore a change in direction. Okay, there's two fundamental kinds of lenses. The first is convex, and these are known as converging lenses. Think magnifying glass. And these lenses are always fatter in the middle and thinner at the edge. The other is concave or diverging lenses. And if you recall, for mirrors, we had concave and convex mirrors as well. All right, first of all, you're going to need to do a principal axis, just like we did with lenses. And this is the principal axis. And if you recall, if you take a chunk of a sphere out and polish it on one side, it would be a mirror. Well, let's say it's a glass now, and you take a chunk of it out and you face it one direction. That's going to give you convex on both sides. You face it the other direction, you have concave, and this line goes from the center of the sphere to the surface. And there will be focal points, but now since light goes through, there will be focal points on both sides. Any ray coming in parallel to the principal axis on a converging lens will end up going through the focal point. Whoa, sounds a lot like what we had with the mirror, except it would bounce back through the focal point. And that is going to be the same thing for this guy. Any rays that come in parallel to the principal axis for a diverging lens, you lay your ruler on the near focal point and it diverges the light rays, so they will be spread apart further. And I think you can start to imagine that a concave lens kind of behaves like a convex mirror, and a convex lens behaves a little bit like a concave mirror. Okay, now there are three possible rays you can draw. There was actually a third one with the mirrors, which we didn't go over, but ray 1, parallel to the focal point, goes through the focal point on the far side. Now in this case, recall, light rays go through lenses. That's how they're designed. So when the light ray hits the center of the lens, you can just draw a line then through the focal point. Ray 2, I love to draw because you never have to lift the ruler. It starts at the same point on the object. Remember, you're getting diffuse reflection off of this guy. Goes through goes through the center of the lens at the principal axis, and it is unchanged. Then the third ray goes through the front focal point and comes out parallel. So, first ray, parallel to the principal axis. You can use a straight line if you want when you're doing ray diagrams for the lens. I just happen to have them drawn here to show you. It's going to go through the focal point, as we talked about. So this would be ray 1. Ray 2 through the center, unchanged. So center of the lens, right there. That is all you need in order to locate the image. If this is the object, the image now is going to be over here. That's the top of the image. It's the top of the object, so those two would be right there. If you're to draw a third ray, it should end up in the same spot through here, parallel to the principal axis, and sure enough, it goes through kind of parallel to the principal axis. Okay, This is when the object is located beyond the focal point. Now, if the object is beyond twice the focal point, which, if you recall, would have been the radius of the um, mirror, then the image is smaller than the object. So this guy looks a little smaller. It looks like it's just beyond. If it is between 2f and f, then the image is magnified. But both of these are inverted. So you're going to get an inverted image. Oh, the other thing, real images are over on the far side of the lenses because light rays go through. This is a real image, and then you have to decide whether it's magnified or not. So here's our image. Very similar to what we did with mirrors. Okay, now what if you have an object inside the focal point? All right, and this is again with a converging mirror. Okay, first ray, parallel to the principal axis. Boom. Then it goes through the focal point on the far side, just like we've done this before. I'll put a little dash here so you can see it. And off it goes on its merry little way. Now, I'm going to dash this guy just for a measure of correctness, because the next one, when it goes through the center of here, you can see that these two rays will never meet on the far side of the lens. So therefore, you're going to get an image formed behind this guy back up here. And the image is going to be here, and it's going to be in a virtual image because these are not actual light rays. So if your eyeball's over here, you're going to see this image back behind it, and it is going to be upright, it's going to be virtual, and it will always be enlarged. By the way, if you were to draw the third ray, you would go like this through the focal point, up, up until you hit, and then it comes out parallel to the principal axis like this. But again, you'd have to extend it backwards to find out where it meets. And again, they all meet at the same locale as they should, and that would be the image. So you're going to get two kinds of images with these lenses, converging lenses. Whenever you have the object outside the focal point, it's going to be inverted and it's going to be real. If it's a real image, you can put it on a screen. So think movie screen, for example. And then whether it is larger or smaller depends upon if it's beyond 2f or between 2f and f. Okay? And you get magnification if it's between 2f and f. If you've got the object in front of the focal point, you get a virtual image which cannot be put on a screen. And so that is the difference between these two. Okay, one other kind of lens, and that is the diverging lens or concave lens. And again, there's two focal points. One on this side for this part of the lens and one on the far side for that part of the lens. And they're going to have similar sorts of behavior. Hey, Karan, did you just show up? Oh, good. Hey, Abhi and Nikhil, would you guys stop talking? Okay, here we go. So the first ray, parallel through the principal axis. And then in this case, I lay it through the near focal point, and it's going to diverge. Now, the reason you use the near focal point is because it's diverging, so you have to lay your like that, like it's going to be through there. And just for grins, let's dash that line as well. Second one, through the center, unchanged. It's going to go like that. Now again, so this is ray 1, this is ray 2. You can see these two rays are never going to meet on the far side or the light side of the lens because they are diverging. If you wanted to do the next one just for grins, The third one, you lay your ruler at the far focal point, and it comes out parallel to the principal axis, like so. And again, you would dash it backwards and see that it meets at the same spot. So here is where the image is going to be. For these lenses, you always, always, always get an upright, virtual, reduced in size image. Just like for the convex mirror, you got an upright, virtual, reduced in size image, and it does not matter where you put it. Okay. Oh shoot, I forgot to leave you a spot for the lens equation. So let's write it in right here. Okay, you ready for this? This is going to complicate things so much. The lens equation looks an awful lot like the mirror equation. Same equation. Now, here is the only little difference. XO is always considered positive, but the image is positive on the right-hand side and negative on the left-hand side. So it is a little bit different than what you did with mirrors. Just think where the light is supposed to go. The light is supposed to go through the mirror, and so you'll get same equation. Object distance is always positive. Xi is positive on the right side, and it's negative on the left side. The focal length is positive for convex mirrors, so these have positive f up here. And for these guys, the focal length, the concave mirrors, it's considered negative. Okay? So that's a little bit of different convention than what we used for the mirrors. But again, typically where light's supposed to go, reflected back off of shiny mirrors, it's positive. Through lenses, it's positive. Other side's negative. Okay. There's something that can happen. It's called chromatic aberration. And if anybody's ever used really thick glasses, you can sometimes get it. Lenses act like prisms, right? Remember, a prism is the old pyramid, and Isaac Newton found that it separates light into colors. Well, when you think about a lens, up at the edge, it functions like a little bit of a prism. And so occasionally you can get a little bit of a ring of color or kind of rainbow around an object. So you can correct that by using so-called achromatic lenses. And really they're just combinations. They're two different lenses that are put together. And the way you do that, and this is on page 506 by the way, is you can add to a convex lens a concave part up here, and so you will prevent chromatic aberration up here at the tip of it. So you just put a convex and concave together as needed. Okay, let's stop there for now. So we've got two lenses, convex, converging, concave, diverging. The ray diagrams, similar to what we did for mirrors. For the concave, there's always going to be three rays, parallel to the principal axis, through the focal point on the far side, through the center, unchanged, just keep your ruler in place. And the third one would be through the focal point on the near side, out parallel. The ray diagrams will show you where the image is. For objects located beyond the focal length, they're always inverted and real. The size depends upon how far back beyond that it is. For an object inside, you always get an inverted, enlarged, upright, virtual, enlarged image with convex lenses. For concave lenses, does not matter where you put it. First line, parallel to the principal axis, then you have to lay your ruler through the near focal point, it diverges. Second one, through unchanged. Where they meet is where the image is.